Alright guys, welcome to the Unit 8 review. So I have all the answers on here. I'm going to go over them really quickly, so if you need to go over something again, go back or pause or whatever. Alright, so number 1, if two objects touch at different temperatures, which direction will the heat flow from the warm to the cold? Heat always flows from the warm to the cold. Number 2, list all that you know about exothermic and endothermic reactions. So some things you probably need to know. Exothermic releases heat, has negative delta H, and the graph kind of looks like that. Endothermic absorbs heat, has positive delta H, and the graph looks like this. There's more stuff, but that's the important stuff. Alright, number 3. Condensation, evaporation, boiling, freezing, exo, endo, endo, exo. Number 4, what happens to the temperature as water boils? It stays constant during boiling because the heat is going into the phase change, not the temperature change. All right, number 5, how many joules of energy are required to increase the temperature of 80 grams of water from 35 to 40 to 39? So we have Q equals Sm delta T because it's the temperature change of a pure substance. So we got Sm delta T, and we round to 1 sig fig because this technically has 1 sig fig when you subtract. This also has 1 sig fig because there's no decimal. So it's 1339 rounded to 1,000 joules. For number 6, we got Q equals Sm delta T as well, because what's the specific heat capacity for a material that has 120 grams absorb 3,000 joules and increase the temperature from 10 to 25. So again, 3,000 only has 1 sig fig. I should probably go back and look at the sig figs for this. So we solve for S, and S is 1.6 joules per gram degree C, but that rounds to 1 sig fig, so that's 2 joules per gram degree C. Alright. Number 7, sketch the heating curve for water. You guys can do that. Number 8, for this one, we have how many calories of energy we required to melt 65 grams of water. So we got 65 grams times 80 calories per gram, so we got 5,200. Right, so that's 2 sig figs. 9, same thing, how many joules of energy we released as 12 grams of water freezes. So this time we got 12 grams and 80 calories per gram. So we got 960 calories. Number 10, I burn a 0.58 gram sample of food and use the heat to melt 26.4 grams of ice. How many calories per gram does the food contain? So we use Q equals M delta H because it is a phase change. So the grams are 26.4 grams and it's melting, so it's 80 calories per gram again. So we have 2 sig figs, because this has 2 sig figs. When we multiply these two together, we get 2112 calories. Divide that by the number of grams, and you'll get calories per gram. So it's 3,641 calories per gram, so that's 3,600 rounded to 2 sig figs calories per gram. We could change it to kilocalories or food calories, but I didn't ask you to, so you don't need to. All right, looking at number 11. For number 11, we have Q for the system is equal to Q for the negative Q for the surroundings, right? Everything with a calorimeter. We're going to start with that equation. So what is the heat capacity of the calorimeter? So we have Q for the hot water is equal to negative Q for the water plus Q for the calorimeter. Since hot water is a pure substance, we use Sm delta T, and cold water is a pure substance, Sm delta T. The calorimeter is an object, so we use C delta T. So we got Sm delta T for the hot minus Sm delta T for the cold, and C delta T for the calorimeter. We solve for both. This one has 2 sig figs as well, so it's 2 there. So when we subtract, though, we get down to 1 sig fig, and we divide that 1 sig fig by the temperature change. So we get down here 86.7 joules per degree C. So rounded to 1 sig fig, that is 90 joules per degree C. Then number 12. Number 12 says, I place this much into a calorimeter, hot metal into calorimeter. It has this heat capacity. So again, we got Q for the system equals negative Q for the surroundings. Q for the metal, again, is equal to negative Q for the water plus Q for the calorimeter. So Sm delta T for the metal is equal to negative Sm delta T for the water plus C delta T for the calorimeter. This time we know everything except for S for the metal. So we got 68 grams. We got 96.9 degrees C. Oh, sorry. That should be negative, but I canceled out the negative for both sides. Then we got 4.184, 130, and then 3.1 degrees Celsius for the water and the calorimeter, and the C for the calorimeter. So we crunch all that together, and then we divide by 68 and 96.9 degrees Celsius, and we get a very low number, and that's fine. We get 0.034 joules per gram degree Celsius. All right, number 13. For number 13, I burn 3.18 grams of material with a combustion of negative 78.3 kilojoules, and a bomb calorimeter, the temperature rises by 13.6. What's C for the calorimeter? So again, Q for the system is equal to negative Q for the surroundings. That's for any calorimetry. We're going to start with that equation. We just have to figure out what they are. So because it's a combustion reaction, we're going to use M delta H. And because it's a bomb calorimeter, we're going to use C calorimeter times delta T. So we know how many grams we have. We also know the delta H. Luckily, the delta H is in kilojoules per gram because it doesn't tell us what the material is. We couldn't convert to moles, so luckily it's already in kilojoules per gram, so the grams cancel out. Then we have negative C for the calorimeter times delta T, so we divide both sides by the delta T, and those negatives cancel out over here and over here. So we get C for the calorimeter is equal to 18.3 kilojoules per degree Celsius. Then number 14, again, it is a calorimetry problem, so we start with the same equation. And it's a combustion again. This time we're combusting PVC plastic, which you should not do unless you're in a well-ventilated area, and even then it's bad for the environment, so just don't do it anyway. So we got M times delta H equals negative C cal times delta T, and it is the same calorimeter, so it has the same C, and the temperature went up by 1.95, and we know the grams, we just don't know the delta H. So we know everything here except for delta H. We divide both sides by the grams. Now, I didn't tell you whether I wanted it in kilojoules per mole or kilojoules per gram. Well, since I didn't tell you the formula for PVC, the only one you can do is kilojoules per gram. So when we divide these things, we get negative 43.4 kilojoules per gram. All right, number 15 was really hard because some people did not actually do the combustion. So if you look at the problem says, use Hess's law to determine the delta H for combustion of 1 mole of CH4. Well, combustion is the thing plus oxygen reacts to form carbon dioxide and water. That is combustion. And then we balance the reaction by adding stoichiometric coefficients. So that's what we're trying to balance. We're not trying to balance some kind of thing, this first one using these other two. So we have the first one, right? We need CH4 in the reactants. So we reverse that first one. We reverse A, because A has it in the products. So we reverse that first one. Then we know that we need oxygen in the reactants. We'll see if that shakes out later. We know we need carbon dioxide in the products, so we use B. And we know we need 2 waters in the products as well. So we use C, which already has 2 waters in the products. So then we cancel stuff out. The carbon and the carbon cancel out. The 2 hydrogens and 2 hydrogens cancel out. So left we have CH4 plus 2 O2s reacts to form CO2 plus 2 H2O, which is exactly what we want. So we add all 3 of these up, and we get our reaction, and we get delta H equals negative 891 kilojoules. All right, number 16, do the same thing, but use bond energies. So it's not going to come out exactly the same because bond energies are just an estimate. So again, we use the reaction, and we have to draw it this time. So CH4 looks like this, the 2 oxygens look like this, the CO2 looks like this, and the 2 H2Os look like that. So the general form of the reaction is bonds broken minus bonds formed. So bonds broken, we have to break all these bonds, and then we have to form all these. So we have 4 C to H bonds that we break, and these are each 414 kilojoules, and 2 O to O bonds, or O double bond O bonds, that we have to break, and those are 498.7 kilojoules. And then we subtract the bonds that we formed, 2 carbon to carbon double bond oxygen bonds, which are 799 each, and 4 H to O bonds, which are 460 each. So we add those things up, and we add those things up, and we subtract the 2, and we get a delta H of negative 784.6, which is not that close to the delta H we got in the last problem, because those should have been exactly the same. That's why bond energies are just an estimate. All right, number 17, entropy, the level of disorder or chaos in a system. So that's the definition of entropy. Number 18, delta S is positive when there are more moles of gas in the products than there are in the reactants. That's the only thing we know so far that makes delta S anything. Look for the moles of gas, whether it's in products or reactants, excuse me, then you can know whether the delta S is positive or negative. Yeah, that's it. And then delta G is positive when the reaction is non-spontaneous. Delta G is negative when the reaction is spontaneous. So a reaction that has a positive delta G is not going to happen. The reverse reaction is going to happen, but the forward reaction is not. We'll talk about forward and reverse reactions next unit. And then number 20, which was really similar to the warm-up, I didn't realize they were exactly the same. If a delta H is positive and delta S is positive, then under what conditions is it going to be spontaneous? Delta G will be negative if the temperature is high enough, because we're maximizing the second term. And if you have a number plus a bigger, or number minus a bigger number, you'll have a negative delta G. And we can make sure this number is bigger by making sure temperature is high. Okay, so that's about it. Yeah.